In Module 5.7, we turn now to the compound option valuation model. We'll be looking at this model within the context of geometric Brownian motion. I've actually worked on an arithmetic Brownian motion version of it, but it's not presented in this book. And so we're going to review some of the basic assumptions of the GBM-based compound option valuation model. Once again, we'll address the question of dividends, which is often not addressed with compound option models. We'll explain the model in detail, review selected plots and related R code. There is quite a bit of complex calculations required in order to compute a compound option value, but it remains a relatively quick calculation. So what is a compound option? A compound option is simply an option on an option. Because of this complexity, we need some different notation. We have multiple expiration dates, and we'll look at a few selected plots. Once again, just highlighting the link between the underlying GBM and some of the resulting graphs. So the compound option is an option on an option. There's two different dates. T1 will denote the compound option's expiration date. T2 is the underlying option's expiration date. And little t will be the valuation date. So standing at little t, we could buy a compound option that expires at T1, and the underlying option expires at T2. And so there are two different strike prices. One is the strike price of the compound option, and the other is the strike price of the underlying option. I have actually run into this, the need for a model of this nature in a variety of different consulting contexts. And one was an interesting bid, as I recall, on the liabilities of a failed bank. And the other bank had to give a bid. It had to be a firm bid for 30 days in order to acquire the liabilities. And so once you made that bid, to hedge the interest rate risk implied, it was a lot cheaper to consider a compound option as opposed to just a plain vanilla option on interest rates. And so this could crop up from time to time. It's a useful valuation methodology for option-based instruments to be able to pull out from time to time depending on what your needs are. Again, the three important dates: compound option trade date, the expiration date of the compound option, and then the expiration date of the underlying option. And so some of the results of the model, it turns out there are four different types of compound options. There's a call on a call, which is a compound call option on an underlying call option. And the upper and lower boundary conditions can be derived. And the valuation model presented here is, this looks similar, but if you'll notice, the upper bound is not linear. The lower bound is actually, sometimes it's not linear and has different convexities. And so a call on a put is a call option to buy a put option. And as the stock price goes down, that call option actually increases in value. It takes a while to get your mind around something like this. A put option on a call option, again, as the stock price declines, the put option on the call actually goes up. And then finally there's a put on a put, and it looks sort of like a call on a call, but the boundary conditions are definitely different. And so these are four unique applications. Really, the only application that I've run across frequently is a call on a call. For example, as we mentioned before, you can view a call option on a stock as if you view stock as a call option on the firm, then a call option on the stock is a compound option on the firm. That's probably the most widely used application of this type of technology. The time values of these compound options, this should begin to look familiar. The positive, the more mass as stock prices go up reflects the implicit log normal distribution. And that's an empirical question on whether that's the right way to go. Perhaps, if in fact the empirical evidence is negatively skewed, then you may want to consider an arithmetic Brownian motion version. Some of the quantitative material, again, this is going to get quite technical, and I don't want to spend a lot of time on the technicalities in this presentation. You're welcome to examine the materials made available in Chapter 5 to look at this in detail. Just by way of reminder, a plain vanilla call in this context is simply a call option that expires at time 2. The payoff is the underlying minus the strike price of the underlying option. The put is just the strike price minus the underlying. And so this is symbolically changed for the compound option. A compound option at maturity, notice its maturity T1. And so a call on the call or a call is simply the maximum of 0 or the value of the call option at T1 minus the exercise price of the compound option. A kaput or a call on a put is the put minus the compound option strike price. Pcall is a put on a call, which is the strike price minus the call. And a put or a put on a put is the strike price minus the put. And so these are the boundary conditions. If we're going to introduce an indicator function, again, we would rather build one model that values all 4 of these options as opposed to writing 4 separate pieces of R code. And so the iota C is the compound option indicator function, +1 if the compound option is a call, -1 if the compound option is a put. Iota U is the underlying option indicator function, +1 if the option is a call, and -1 if the option is a put. And so it should be clear there are 4 different possible combinations. The compound option is a call, the underlying is a call or a put, the compound option is a put, the underlying is a call or a put. Some of the notation is very similar. The ST is the underlying instrument. Sigma is the volatility of the underlying instrument. Delta is the dividend yield of the underlying instrument. Q hat is the yield on the underlying option. If we let the firm value be the underlying, then the stock is the option. Note that delta does not equal Q hat as debt requires payment. And so this Q hat, in the context of a call option on a stock being a compound option, Q hat is the dividend yield on the equity of the firm. Delta is the all-in cash flow yield from owning the firm. So owning the firm, I get both the dividend yield as well as interest on debt. And so these 2 numbers are not the same. Most compound options ignore the yield on the underlying option, but that poses some significant problems because if I'm trying to apply this to equity, then I've got to deal with the fact that equity often has a dividend payment. We'll use B subscript with these subscripts as simply being a present value function. And so the underlying boundaries, again, I'm not going to take the time to go through the details, but you can derive the underlying call lower bounds and upper bounds in a singular fashion with this kind of notation. It turns out the calls on puts or calls, the boundary conditions can be expressed in this fashion. Again, you can see the derivations in the write-up in the materials provided. Puts have a similar set of boundary conditions. And there's actually put-call parity that could be deployed. Remember, with a dividend, with a yield on the option, it turns out that I've got to make some adjustments to the parity conditions. but a call on a call minus a put on a call should equal to this representation. Call on a put minus a put on a put should equal to that. And then the combination of the two should equal to this boundary condition. And so just like underlying options on stock, compound options have a whole set of boundaries as well as parity conditions. The model itself can be written as a complex function of these these iota terms, as well as, if you'll notice, rather than being a univariate CDF of a standard normal, it's a bivariate CDF of a standard normal, and there's a correlation coefficient. And so clearly, and this has 3 terms and not 2. The last term looks sort of familiar in the context of the Black-Scholes-Merton. It's the present value of the compound option strike price times the univariate CDF. But these other 2 terms are going to require the use of a bivariate CDF approximator. There are 4 different D terms. There's D sub 1,1, D sub 1,2, D sub 2,1, and D sub 2,2. And so there'll be 4 different calculations required. If you'll notice for D21 and D11 that the was playing what typically is the strike price is going to be a equilibrium stock price under certain conditions. The conditions are given here. What is the equilibrium stock price that makes the call option or the option at the expiration of the compound option equal to the compound strike price? And so once I've solved for that implied parameter, I can easily use it to compute the other parameters needed. The critical stock price is this S star, and the code to get to that is basically provided within the materials. And again, I don't want to take the time to go over code, but each one of the D calculations are provided. We build a function that calculates the critical stock price. We examine the results. The compound option value is simply the combination of calls to the D11, D21, D12, and D22. With these results, I can input this into a bivariate standard normal CDF and get these 2 terms, and then I can easily compute the compound option value. And so with some sample inputs, we can provide some sample outputs, and you can examine this at your leisure to make sure you understand how it works. To get these graphs to work, it was a little bit tricky to find the midpoint where what I'm looking for is when the lower bound actually breaks off of 0. And once I have that, I set the midpoint. And it turns out to graph compound options is fairly tricky. You'll find this very helpful to center the graph on where the lower boundary actually breaks. And then setting the y-axis in a similar fashion. And so in summary, this was an extremely brief introduction to the GBM-based compound option valuation model. There are 2 versions of dividend, discrete, and compound. We examined primarily the continuously compounded version. It turns out that the model presented in this material is an extension of what's in the published literature in the sense that we can address cash flow yields on the underlying option, which in the prior literature really isn't addressed that well. And we examined a few plots. We noted that the time value plots reflect the log normal distribution implicitly assumed in GBM, and that should be a red flag. You should be concerned and use this model carefully, particularly when the input volatilities are extremely high. And so this concludes our brief tour through options, and we'll turn next to futures and swaps.